I'm Pete Shadbolt. I'm a co-founder of PsiQuantum. I've worked on quantum computing for probably just over 10 years now. I started out as an experimentalist at the University of Bristol, building and testing, small quantum chips, showing that we could build qubits and run algorithms and all the sort of basic scientific demonstrations. I went from there to Imperial College, where I worked on the theory and the architecture of these machines and how we're going to make them fault tolerant, how we're going to run error correction. And it was there that we really kind of hatched the idea to found this company and move to Silicon Valley. And I've been living here ever since, doing all sorts of different things associated with building a company, from technical stuff to outbound facing stuff and everything in between. Yeah, so I think the first thing to do is to make a good distinction between supercomputers that are calculating things for scientists, basically, and data centers and server farms, which are running your social media and your business applications and whatever else. They are quite similar. If you looked at a photograph of them, they would look pretty similar. Racks of modules with CPUs and GPUs and memory and whatever else. They're both building-sized machines. But if you look at the carbon footprint and the power consumption of these things, of course, it's dominated by the commercial business applications, as opposed to the scientific applications and simulation problems that we're talking about here, which are a pretty small fraction of the total power consumption of these big machines. But then if we look at the supercomputing category, what problems are those guys solving? It's almost entirely simulating physics or chemistry. There's a few exceptions to that, where large financial organizations have their own supercomputers to do Monte Carlo simulations of markets, for instance. But yeah, I think the sort of de facto standard use for a supercomputer is to simulate physics or chemistry, and that means fluid dynamics simulations. It means computational chemistry, calculating the properties of molecules, things like liquids, plasmas, reaction chemistry. It's a long list of things, but it's basically trying to avoid having to do tons of experiments and tons of trial and error. And I think, this goes back to the very, very early days of conventional computing. If you look at what people used computers for in the early days, well, they used them for code breaking, Alan Turing and the Enigma machine and so on, famous story. But they also used them for simulation really, really early on, even before digital computing has sort of established itself as the standard. People were building analog computers to do ballistics calculations. So if you want to see where your shell is going to land, given some wind conditions and whatever else, that was like a pretty key application early on for conventional computers. And then there's beautiful sort of stories of, well, people used to design wings for aircraft with a wind tunnel, right? And actually, I was reading the other day, I didn't realize this, but actually the Wright brothers were pioneers of wind tunnel technology when they were designing that first powered flight. They built a lot of experimental wind tunnels, and they were seeing how the air flows over the wings. And of course, now wind tunnels are almost entirely obsolete, right? They're mothballed, and that's because we can simulate fluid dynamics in a computer. It's way more convenient, and you can try out, God knows how many designs for a wing without having to send somebody down to the shop with with some plywood and some sandpaper, right? I think the general theme is simulating physics and chemistry without having to do the trial and error experiments that you would otherwise have to do. Yeah, so when we talk to our customers, we deal with people across, large companies across pretty well every industry: automotive, aerospace, finance, healthcare. When we first engage with them, usually these guys have already been thinking about these questions. What are they going to do with a quantum computer? And the way that we frame it for them is to say, have a think about either problems that you currently know to be impossible, where maybe you're throwing large amounts of time and money at conventional supercomputers and not getting the answers that you need. But also have a think about problems that you are not even trying to solve because you know that they're impossible, right? So that's a little step beyond things that you've already identified to be impossible. And so that's really the first thing to say is that, and I think this is widely understood at this point, quantum computing is not going to give you a 2x speed up on every single computational task that you have. And in general, it's a bad idea to use a quantum computer for a given computational task. And we're really just talking about a small fraction of these simulation problems that cannot be solved by any conventional computer, and where we don't actually ever expect to be able to build conventional computers to solve these simulation problems. And, going back to my previous comments, quantum computing today is at the stage that conventional computing was, towards the end of World War II, right? Where of a handful of applications, whatever, code breaking, ballistic simulation, blah, blah. But you have only scratched the surface of the potential list of things that you're going to do. So we're very much in that regime. We know of a handful of applications. And those generally are trending towards computational chemistry problems that are extremely hard for the efficient classical methods that we know of. So this is a very natural place to look for useful applications of quantum computing, which is to say that molecules are pretty small, right? And they're intrinsically quantum mechanical. And so if you want to simulate a molecule, you're going to end up simulating quantum mechanics. And quantum mechanics is really hard to simulate for the same reason that quantum computers can be really powerful. And so the status quo is that very smart mathematicians have found incredibly powerful, efficient techniques to simulate most of chemistry on a conventional supercomputer. And it's actually incredible how successful those methods like density functional theory have been in allowing you to accurately predict the properties of molecules without the need for a quantum computer. But there is still a whole bunch of problems where you have a particularly tricky molecule or a particularly tricky operating environment where these classical methods completely fall over. They give completely the wrong answer. And to give a few examples, battery chemistry is a classic. So in a lithium-ion battery today, lithium-ion batteries have proliferated into every corner of our life. It's really unbelievable when you start reading into it how poorly people understand the chemistry of these lithium-ion batteries. I actually used to work on polymer lithium-ion batteries many years ago. I used to have my arms in a glove box mixing up chemicals, trying to find new lithium-ion batteries. And the state of the art is not really much more sophisticated than that, because people cannot simulate the chemistry that's happening in there, and they don't understand it. And okay, let's try and design lithium-ion batteries. Well, one way to do it, which is what we do, is go and build a new battery with a different electrolyte, run it for 10,000 hours, see if it catches fire or not, and just keep turning that crank. That's obviously very painful, expensive, and slow. Okay, let's try using a supercomputer. And indeed, if you look inside these big car companies, you find large, well-funded research groups who are trying to use supercomputers to iterate over many different experiments on these electrolytes without having to go and build stuff and see if it catches fire. And the story is consistent, which is that they're spending millions of dollars, they're spending hundreds of hours of computing time, and the answers that they get in the end, they don't really trust, because these classical efficient methods are just not good enough at simulating that chemistry. And so that's one specific example where quantum computing has the potential to allow us to do things, profoundly better than you can do with a conventional computer. Yeah. Human beings have made a catastrophic mess of our own planet, and we are now staring down the barrel of having to actively remove gigatons of CO2 from our atmosphere, right? It's not enough just to do your recycling and whatever else, like put a brick in the cistern. You're going to have to remove gigatons of CO2 from the atmosphere. And, I really think it's fair to say we are staring down an astronomical engineering problem for us to, sustain a good quality of life on this planet. And per my previous examples, when we human beings today try to design materials, catalysts, drugs, when we try to work with chemistry, the analogy is that we are doing that with Stone Age tools today, right? We have incredible breakthroughs in computational chemistry methods that have been very successful, but we still really cannot simulate chemistry properly. And, we're essentially flailing around in the dark with a huge amount of trial and error. And that is, that's a pretty sad situation, especially given the scope of and the magnitude of the challenge that we face. So, the analogy that that Jeremy likes to use is that it's like trying to design an F-35 fighter aircraft with a pocket calculator, right? It's just not going to work. And it's actually very interesting, and kind of it's encouraging and surprising also to me. If you look at the most popular examples of near-term applications for quantum computing, of course there's code breaking. People like to make a big noise about machine learning. It's not really worked out properly yet. The best examples come from chemistry, computational chemistry. And interestingly, the best examples are all very tightly connected to sustainability and climate change applications. So it's a multi-year project in practice to go from a nice idea, like, hey, let's simulate molecule X on a quantum computer, to actually having a recipe that's been properly worked out to do that, having the code, having the algorithms, knowing how big of a quantum computer you're going to need. And those projects have only been run a few times on planet Earth. You need a big team of PhDs in quantum information, and you need a sustained, focused effort to get to an answer. Can we actually do this? Where that has actually been done is by the Microsoft group for catalysts for carbon sequestration. So they've done a beautiful job, 100-page paper, very detailed analysis of how you would use a quantum computer to design a catalyst that you could use to cheaply and easily remove CO2 from the atmosphere. Where else has it been done? Well, also by the Microsoft group for fertilizer. Right now, we burn some fraction of the world's natural gas resources making fertilizer by the Haber-Bosch process. So it's a very high temperature, very high pressure process. You burn a ton of natural gas and you can make fertilizer and feed people. Of course, bacteria in the soil are doing exactly the same thing, making nitrogen fertilizer, and they're doing it at room temperature and pressure. How do they do that? Nobody knows. Can we simulate the chemistry? Not really. And so that's also has been tackled in depth by the Microsoft group. The battery chemistry stuff, we just put a paper on the archive that goes into some detail on how you do battery chemistry on a quantum computer, and that's been looked at by many other groups. So it's actually kind of surprising and exciting to me. I mean, these things could not be any closer really to the problem of sustainability and climate change. And in fact, the other examples that we know of where people have gone deep, there's the code breaking example. So prime factoring with Shor's algorithm. That's about it, to my knowledge. Like, it's quite surprising. The vast majority of times that people have really looked at this in detail, it's been very closely connected to climate change. So what are we going to need to do to make the quantum computing hardware useful? So it's not useful today. There are no useful quantum computers that are really outperforming supercomputers at commercially valuable tasks. And I'll tell you a little story on sort of the past and the future here. When I learned quantum computing 10, 15 years ago in my undergraduate degree, the message was very clear, which is that quantum computers are going to have errors. They're going to have a lot more errors than the transistors in our conventional computers. So the transistor in your cell phone goes wrong, much less than 1 in a trillion times, right? It's 10 to the minus 15 error rate or something like that. You're never getting error rates like that from a qubit. And so in order to run useful applications, we're going to need error correction. We're going to need to continuously correct those errors using something similar to what's happening in the SSD in your laptop or on this phone call here. We're going to need redundancy to overcome that error rate and make these things useful. And you're probably going to need a ton of redundancy, like you're going to need 1 million qubits or so to do anything useful. And that story was like really the sort of the standard message on quantum computing. We're going to need error correction. We're going to need millions of qubits. You can find that in Jeremy's PhD thesis from many decades ago, and it was really part of the curriculum at that time. And then 5 to 10 years ago, there was a change. There was a wave of enthusiasm for the idea that you might get something done without error correction. And the argument was that my laptop can simulate 30 qubits or so. So 30 qubits isn't enough to be useful. But even a gigantic supercomputer cannot simulate and will never simulate 100 qubits or so. So Google have just shown this very spectacularly. Their 53 qubit chip is winning races with building-sized supercomputers. Now, it's winning very artificial races, and it's not doing anything useful, but it's a very compelling demonstration of the exponential power of a quantum computer. And you look at that and you say, well, look, Google have got a chip the size of my thumbnail. It's a controlled system of qubits, and it's winning races with a building-sized supercomputer. That looks like a lot of leverage, right? Like that looks like a powerful device. Let's find a way, let's find an algorithm, find an application for that machine. That was the theory behind this movement for NISQ, so near-term intermediate scale quantum, and for trying to get things done without error correction. And maybe you don't need 1 million qubits, right? Maybe you only need 100. And we were really deeply involved in that. So we worked on the first demonstration of the variational quantum eigensolver, which is one of the sort of poster child algorithms for this kind of idea. We worked on things like boson sampling. We had these small quantum computers, and we got really excited. Like, maybe let's do something valuable without having to wait for 1 million qubits. And so to actually answer your question, what is required to do something useful? If you'd asked people 5 years ago, that this kind of the story was bifurcated, right? You would find people who believed that you need 1 million qubits and error correction. A lot of people were very excited about getting something done with a much smaller machine. I think it's fair to say that that enthusiasm is now diminishing. And that people are really starting to recognize that despite 5 years of searching, nobody has found any commercially valuable applications for machines without error correction. Everything that we know of today requires billions of gates, and you're not getting billions of gates without correcting for errors. So people are still looking, the jury is still out, and it is still absolutely possible that somebody will come tomorrow with an algorithm that you can run without error correction, and will get value from, you know, a whole bunch of different quantum computing technologies very quickly if that happens. Our company was founded on the premise that you're really going to need error correction, and that even if you do find these NISQ algorithms, they're not going to really deliver on the promise of, you know, full-scale quantum computing. So we've invested exclusively in trying to get to that 1 million qubit regime, and to build an error-corrected system. I think we're going to talk a little bit later on about, you know, what are the technical obstacles to doing that. But yeah, let me reiterate, as far as anybody knows today, the requirements to run commercially valuable applications on a quantum computer are that you're going to need error correction, and you're going to need millions of qubits to support that error correction. Yeah. The first thing that you have to do is figure out a model that is based on leverage. And the reason that I say that is that if you look at the academic trajectory for building more and more qubits, it's pretty depressing, right? Myself and my colleagues and people all around the world, you know, there's incredible scientific work going on, but it's taken decades to go from 1 qubit to 50. And so, you know, if we carry on that trajectory, then it's really, you know, many, many more decades to get to a 1 million qubit machine. So the first sort of meta requirement is that you do something different to what universities do, and you do something different to, you know, the science experiments that we have today. Our approach to that is based on leveraging the semiconductor industry. So the philosophy for us from the beginning was, yeah, if I'm, you know, I used to put rubidium ions into ultra high vacuum and shoot them with lasers. Classic science experiment, right? Like pure, you know, physics lab type of setup. And yeah, if you told me that I need 1 million qubits with that system, I would say, yeah, get back to me in, you know, however many decades. On the other hand, you know, my cell phone here, there's 1 billion transistors, right? And the semiconductor industry has invested $1 trillion over 50 years to be able to build those transistors with absolutely mind-bending reliability, process control, uniformity, you name it. I mean, this is really, like, as far as I'm concerned, the peak of technical human achievement on the planet. What goes into your cell phone today is just an utter sort of mind-bending technical achievement. And so Jeremy, our CEO, and the company, you know, we've always been obsessed with this idea that if we could build qubits and if we could build the quantum computer in those same manufacturing processes, 1 million should not be such a big, scary number. I mean, it's like way less than what's in my cell phone here. So for us, one of the big things that we've invested in from a technical point of view is getting our qubits into that advanced manufacturing process. And of course, that's not a trivial thing to do. It's not a question of just, you know, making a phone call and paying your money. These big semiconductor foundries are very, very locked down in terms of what they will and will not allow into that manufacturing process. You know, these guys are not in the business of doing crazy science fiction stuff like quantum computing. They don't like exotic materials. They don't like exotic operating environments. All of the sort of science fiction stuff that you normally associate with a quantum computer is antithetical to the entire operating model of these big foundries. What we've done is we've pursued a photonics approach, where we build our qubits using light, using single photons. And that gets around a lot of those constraints to the extent that we're now building quantum chips essentially shoulder to shoulder with laptops and cell phones in a tier one semiconductor foundry. So we've focused a lot on that, and we really believe that's actually a requirement. You know, our conviction is that whilst you are building qubits in a university clean room or a 200 millimeter R&D fab, it's going to be very, very hard, if not impossible, to achieve the yields, the performance, the number of devices that you need for a useful quantum computer. So that's kind of one pillar of 4 that I'm going to talk about in terms of the obstacles that need to be overcome. Manufacturability, I think, is a huge component here. The other 3 pillars here, which I can elaborate on if it's helpful, are connectivity, cooling power, and control electronics. And I think what's interesting is that none of those are really quantum at all. They're really engineering and scaling problems, and they're the ones that I just listed. They are manufacturability, cooling power, control electronics, and connectivity from my point of view. And so just to summarize those 4, on manufacturability, it's our conviction that you have to build the quantum computer using an advanced semiconductor manufacturing process, or else you're not going to achieve the yields, the performance that you need for fault tolerance. We've invested very heavily in that. On connectivity, up until now, the whole quantum computer is fit onto a single chip. But once you recognize that you're going to need 1 million qubits, that is no longer the case. You're going to have to connect chips together. And of course, you can't just use a USB cable, right? You need a quantum interconnect. That's something that's very, very challenging to build for most approaches to quantum computing. We're fortunate that we encode with photons, and so we can send those photons straight into the same optical fibers that you find in a data center. But there's still work for us to do there, and there's a lot of work to do for the whole industry to figure out how we network these quantum chips together. Cooling power, of course, is a huge deal. All quantum computers today require cryogenic cooling to liquid helium temperatures or worse. And whilst the current systems that we have are quite impressive, we're going to need way more cooling power than anybody has shown so far, at least in a quantum computing context, in order to run a useful machine. And so people are starting to invest in, you know, how do we actually achieve that much cooling power at liquid helium temperatures? And then control electronics is a topic that sounds pretty unsexy and boring, but is actually really quite profoundly important as a technical obstacle to overcome before you build a useful machine. When you've got 10 qubits in a science experiment, you can afford to do all of that control with, you know, FPGAs and rack-mounted gear that sits outside of the cryostat. That's not going to work for a 1 million qubit machine. You need to put CMOS control electronics, conventionals, computer chips pretty close to the qubits in the vast majority of cases to do the care and feeding of those qubits. And that's immediately problematic if your qubits are at 10 millikelvin. So if your qubits need to be at some, you know, 100th of the temperature of deep space or something, you just can't put CMOS electronics at that temperature. And so you got a big problem on your hands. And so there's a lot of investment in how do we run conventional electronics at liquid helium temperatures? How do we interface that to the qubits? And yeah, many groups, Microsoft, Intel, et cetera, are doing great work trying to solve those problems. So yeah, I think to summarize, it's not about the qubits anymore. It's about really engineering problems, scaling problems that aren't particularly quantum at all. Yeah, so it's a great question. You know, we've been through 10,000 wafers worth of silicon. a wafer is, dinner plate size chunk of silicon. We've been through that much silicon already building this thing, and that stuff's going in the trash, right? It's part of the development effort. And as somebody who does, diligently cleans out my baked beans tins and puts them in the recycling, like, that makes me feel bad. Okay, I'll be honest about that. On the other hand, it absolutely pales in comparison relative to, any number of large commercial computer building activities, semiconductor, commodity semiconductor devices. We absolutely pale in comparison. We barely appear on the chart. So given the transformative, exponential type of advantages that we hope to obtain from quantum computing, I think the cost benefit analysis works out in favor of taking that hit. So yeah, absolutely, there will be finite resources used in building these machines. We'll rip through a bunch of silicon, we'll burn off a bunch of liquid helium, but it is a tiny, tiny impact relative to, the vast majority of large-scale industrial activities. Yeah, well, I think, and I'll say something that's maybe a bit provocative here. I think that, capitalists and technologists traditionally have secretly hoped for wars, because wars produce new technology, right? This is a known effect, and that's absolutely the case for conventional computers. And we already talked about this. Look at the early applications, code breaking in World War II, ballistic simulations. It's very clearly driven and accelerated by war. And I think that the observation that you're pointing to is really actually quite nice and encouraging, and also terrifying, which is that our generation has figured out that climate change is way bigger than any war that has ever been fought on this planet, right? Like, it's a much greater existential threat. It's a much greater priority than anything you could otherwise imagine. And so, yeah, developing a quantum algorithm to a level of maturity where you can actually take it seriously is a huge investment. There is a very broad set of opportunities that you could pursue. There's any number of different entry points to thinking about quantum algorithms, and people are obviously choosing to spend their lives and spend their time looking at applications that are relevant to what we believe to be the highest priorities for this planet, and I think that's actually very encouraging. I don't think that's by accident. I don't think there's some law of nature that means that quantum computing is especially relevant for climate change related applications. I think that that's people choosing to work on things that they perceive to be high priority. So that's nice. Yeah, it's very good.